is Crib, and this is a review video for Chapter 4. I put together this PDF. You don't have to print it out. You can just look at it. I will put it out there for you if you want to print it out for some reason. So this is just a periodic table, and I just want you to remember things like helium, for the sake of doing the electron configuration, would be written over here. And this whole section, these two columns right there, are the S block. And the principal energy levels would be written here on the side. And then remember this middle section where the transition metals are, this is the D block. And then this is the P block over here. And when you go from 4 in the middle section, it goes down to level 3 or energy level 3. When you get back over to the P block, it goes back up to energy level 4. So this is still 2 and 3 and 4, 5, 6, and 7. And this is the F block. The ones at the bottom are the F block. Other things that you need to remember, and it's super important to remember these things, are SPDF 1, 3, 5, 7. And that's because, look at this, I just found this, SPDF 1, 3, 5, 7. This shows you, it's blurry, but this is the S sublevel. There's the 1 orbital for the S sublevel. This says individual orbitals. I couldn't find a better picture. So 1 shape. This is the P sublevel. There's the 3 shapes, 1, 2, 3 shapes for the P sublevel. And if you put them all together on top of each other, that's what it looks like. This is the D sublevel. And there are 5 shapes, 1, 2, 3, 4, and 5. You put them all together, they look like that. This is the F sublevel. And there are 7 shapes, 1, 2, 3, 4, 5, 6, and 7. You put them together and they all look like that. It just gets really more complicated. Remember that each orbital, so these are the sublevels of these orbitals. Each orbital can hold 2 electrons. Okay, so the S sublevel has 1 orbital. 2 electrons is all it can hold. The P sublevel has, these are the 3 individual orbitals. That's what that says there. Orbitals. There it is. Orbitals. There we go. So the P sublevel has 3 orbitals, and each can hold 2 electrons. So I could draw an electron here and here. 2, 4, 6 electrons. So 6 electrons can fit in the P. The D sublevel can hold 2. So 2, 4, 6, 8, 10 electrons. 10 electrons could be in the D sublevel, and it's 5 orbitals. And the F sublevel could hold 2, 4, 6, 8, 10, 12, 14 electrons. So SPDF, this is how many orbitals each sublevel has, and then times 2 is how many electrons. So that would be 2, 6, 10, and 14 electrons in those sublevels. It's important for you to get those numbers correct. So we have sublevels, and inside the sublevels, the next level would be in orbitals, and each orbital can hold 2 electrons. So S sublevel, 1 orbital, 2 electrons. P sublevel, 3 orbitals, 6 electrons. D sublevel, 5 orbitals, 10 electrons. F sublevel, 7 orbitals, 14 electrons. So make sure you get that straight. All right, now what we're going to do is go ahead and review electron configuration and orbital notation. But when we're doing that, we have something called the Aufbau principle. I told you I might show you a graph. Here's a graph of energy. Energy would be like in joules. And so the Aufbau principle basically says we have to fill the lower energy levels before the upper ones. So notice that energy level 1 has less energy than less S2 and then the SP. And then S3S and the 3P. But notice this. See how the 4S has slightly less energy than the 3D? So that's why we fill the 4S before the 3D. And then 4P has slightly more energy after that, so we fill that next. Now that we do that automatically by following the periodic table. So I'm going to do a few examples. I'm going to erase this just because I want to have room to do it up here. And I want to write again, that this is the D block, but I'm just going to write it on top. Sorry, right there. Let's write it on top. This is the D block in big letter, big. Okay. All right. Now let's figure out the electron configuration for one of these elements. Let's go ahead and pick something weird. This right here. Okay, element 41. Right, 41 is its atomic number. That right there is the atomic number. Remember, the atomic number is the number of protons. And if it's neutral, it's also the number of electrons, because it has to have the same number of positives as negatives. To do the electron configuration, we go up one level right above it. So go up right above it, and then we go to the very end, krypton. Krypton had this one right here, which I can't even see for sure. Niobium, I think is what it's called. But krypton has a bunch of things. It has 36 electrons. This contains everything that krypton contains. So we put krypton in brackets, and now we're going to add the extra stuff. So we're at energy level 5 now, and we're here, rubidium, and this would be in the S block, because the S block is all these elements in these first two columns. So S1, S2, so 5S2, and then we at energy level 4, and we're in the D block, and we just count until we get there. 1, 2, 3, 4D3. So this is the electron configuration. It's a way of showing the arrangement of the electrons, and now we're going to draw the orbital notation. Remember the SPDF 1357, S has one shape. D has 1, 2, 3, 4, 5 shapes. The S here has 2 electrons. Hund's rule says to spin up before you spin down. And so this one has 3 electrons. Hund's rule says put 1 in each spot before you double up. So 1 electron here, here, and here. These 2, we have to show that they're empty. There's nothing there. Nothing's doubled up. And electrons go in these different shapes so they get away from each other, because they're likes. They're all negatives. And negatives are repelling. They're trying to get away from one another. If this was in a box, sometimes you see these in boxes, it would be 1, 2, 3, and 2 empty boxes. That's what the D is for. Okay, I hope you did that one. I'm going to give you another one. I want you to try to figure out, following the same example, give me the abbreviated, that's what this is, the abbreviated electron configuration. So abbreviated will have something in brackets. The abbreviated electron configuration for, let's see, how about, not that one. How about, copper, Cu. The abbreviated electron configuration for copper. All right, I'm going to give you a few minutes. I want you to write it out, and then we're going to check it. You're going to enter it into the computer as well. I wrote out copper. First of all, notice that we go to the end to argon. So I just go up a level to the very end, it's argon. And then we go down to energy level 4, and it's the 4s 1 and 2. And then we go to energy level 3, and we have to count 1, 2, 3, 4, 4D4. And then if we want to do so that's electron configuration. All right, now I want you to pause the video and do the orbital notation, and then write it on your paper, and I will write it here. Okay, I'm going to assume that you've done it. So 1 shape for S, and for 5 for D's. 1, 2, 3, 4, 5, 4 electrons. 1, 2, 3, and 4. So that's the orbital notation for copper. All right, now I'm going to ask you a couple of questions about which element. So I'm going to pause the video and put the questions on the board. All right, this is an electron configuration of an element. I want you to see if you can figure out what the electron configuration, what element this belongs to actually. So what we do then is we look at this, and we see that it contains, whatever it is, it contains krypton, and then it goes to the 5s2. That's what this is. The 4d10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the 5p, we go back up to 5, p5, 1, 2, 3, 4, 5. So this is for iodine. Okay, now what about the orbital notation for this element? I'm going to draw lines. It'd be an S, so one S up, and then the D, 1, 2, 3, 4, 5, and 2, 3, 4, 5, 6, 7, 8, 9, 10. And the P has three shapes, three lines, 1, 2, 3, 5 electrons, 1, 2, 3, and now we double up 4 and 5. That one only has 1 in it. That would be the orbital notation. Okay, we're going to try one more. I'd like you to look at this one. Here is the orbital notation, electron configuration. I want you to figure out which element has this electron configuration and enter it into the computer. All right, after you've answered that question, we're going to go on to more review. So we look at the orbitals, SPDF 1, 2, 3, 1, 3, 5, 7. I showed you the Aufbau principle. We've actually done some examples now. So we're going to talk about isotopic notation and Lewis dot notation review. Remember in isotopic notation, the number at the top, whatever that is, like 260, this would be the mass number. And the mass number is protons plus neutrons. The bottom number might be 151. That would be the atomic number. And the atomic number is equal to just protons. Okay? And if it's neutral, it's also equal to the electrons. So this element would have 260 would be its proton count plus its neutron count. So how many neutrons does it have then? We'll just subtract it. 260 minus 151. Okay? How many neutrons is that? I'll just do it on the calculator so I don't make a mistake. 260 minus 151, 109 neutrons. Okay, I could have just done it right here, 109 neutrons. Okay, so it has 260 protons, it has 109 neutrons. How many electrons does this have? It also has 260 because the proton count equals the electron count if it has no charge, and this has no charge. We're going to be dealing with ions more in a bit. So that's isotopic notation. So if I have a new element called, I don't even know, just element Y. All right, an element Y has 400 electrons, and it has 200 neutrons. Well, what number goes down here at the bottom? Well, if it has 400 electrons, it has 400 protons. So that's the atomic number at the bottom. If it has 400 electrons and 200 neutrons, that's going to be 400 protons and 200 neutrons. So 600 is the mass number, and that would go at the top. So that's isotopic notation. Keep that in mind. All right, now we're going to do Lewis dot notation. So I'm going to look at the periodic chart again at the top. And I'm just going to write them up here so we can just refer to the periodic chart. So what is the Lewis dot notation? Well, first we have to review valence electrons. Remember, valence electrons are the outermost electrons. For instance, beryllium, right there, element number 4, it has atomic number of 4. That means 4 protons. The first 2 electrons are in energy level 1, and then it has 2 electrons in energy level 2. So that's energy level 1 and energy level 2. And if you look at the electron configuration for beryllium, it would be 1s2 and then 2s2. This number is the highest energy level, and it has 2 electrons in the highest energy level. There they are. So these 2 electrons right there and right there are in the 2s2. They're farthest away from the nucleus. They have more energy. Remember, the farther they are from the nucleus, the more energy they have. So the 2 valence electrons are what you put when you do the Lewis dot notation. You just write the symbol and draw electron number 1, electron number 2. That's the neutral atom. All right, now let's look at another one. What about silicon? Silicon is column 14 or 4A. Remember that silicon has an atomic number of 14. That means there is 14 protons and 14 electrons in the neutral atom. How many valence electrons, though, does it have? Well, it's in 14 or 4A, so it has 4 valence electrons. Everything in this column has 4. Carbon has 4, germanium has 4, tin has 4 valence electrons. So how do I write silicon's Lewis dot structure? Silicon and then 4 electrons. 1, 2, 3, 4 electrons around it. Okay, we're going to put up a few more for you to do, and you're going to answer them by putting them into the computer. So how many valence electrons does phosphorus have? How many valence electrons does phosphorus have? All right, it's in column 15 or 5A, so how many valence electrons does it have? Enter that in. Well, 15 or 5A means it has 5 valence electrons. How many valence electrons does chlorine have? Well, it's in column 17 or 7A. So how many valence electrons does it have? Enter that in. It has 7 valence electrons. All right, so draw the Lewis dot structure for chlorine. Chlorine with 7 dots. 1, 2, 3, 4, 5, 6, 7. Chlorine has 7 dots around it. Fluorine would have 7 dots around it. Bromine would have 7 dots around it. What about krypton? Krypton is in column 18 or 8A, so it has 8 valence electrons. So it would have 8 dots. 1, 2, 3, 4, 5, 6, 7, and 8. Krypton has all 8, the octet, so it's a happy atom. It's not going to share them or transfer them. Okay, so I hope you remember how to do the Lewis dot structures and the isotopic notation. We're going to review multiplication of units because some of this was missed. When we multiply this, I want you in this case to turn everything into centimeters. Okay, so we have centimeters here. You can't multiply unless they're the same unit. So we have to do unit conversions first. So 5.1 meters, we have to remember the relationship between centimeters and meters. There are 100 centimeters in 1 meter. Centi means 100th, like a penny. And so 100 pennies in a dollar, 100 centimeters in a meter. So I want to turn it into centimeters, so 100 centimeters would be on top, and 1 meter would be on bottom, and I cancel out meters. So this times that is 100. Multiply this times this. 5.1 times 100, that's going to change this number. So I really don't have to do another step here, it equals. So 5.1 times 100 would be 5100. We have 2 significant figures in this number, so we have to keep 2 sig figs in that number. You have the 1 has to be in the 100ths place, so this becomes 5100 centimeters. All right, now we got to turn millimeters into centimeters. Well, what's the relationship there? There are 1,000 millimeters in 1 meter, or we could say there are 10 millimeters in 1 centimeter. This one is the most convenient, 10 millimeters in 1 centimeter. You need to memorize that, 10 millimeters in 1 centimeter. So 567 millimeters, that's my known. I multiply it by the conversion factor. I want centimeters, so 1 centimeter and 10 millimeters on the bottom. So I just divide by 10. So this is 56.7 centimeters. So 56.7 centimeters. This first number has 3 sig figs, so this has to have 3 sig figs. Now all the units match, and we can actually multiply them. So I'm going to pull my calculator back up, and let's multiply these numbers. We have 46.7 times 5.1 times, no, not times 5.1, back up, 46.7 times 5,100. There we go, 5,100. You see that's the unit conversion we did right there. 5,100 is what we use, times the unit conversion 56.7. So there's that number. That's the raw number, 13504239. 13504239. 4239, yes. 4239. Now we multiplied centimeters by centimeters because we got rid of that. By centimeters because we got rid of that. So centimeters times centimeters times centimeters is centimeters cubed. That's my unit. Now I have to fix the sig figs. I have 3 sig figs, 2 sig figs, 3 sig figs. 2 sig figs is the smallest amount. I need to round to 2 sig figs. You always come in from the left. I have to round to this number. So that, look at that, that's a 5. That causes the 3 to round up. So it's 1, 4. And then I have to put a 0 where all these other things are, because the 4 has to be in this position. It has to be right there. So 1, 2, 3, 4, 5, 6 zeros. 1, 2, 3, 4, 5, 6 zeros. Centimeter cubed. Now that might be the answer, but it'd be more convenient to turn that into scientific notation. So I'm going to do that. The decimal would be way down here. Now notice again, this is, let's see, 14 million. This is 13,504,239. 13 million. The 4 needs to be in the millions place because that's where the 3 was. You can't just drop numbers. Now let's put in scientific notation. The decimal's here. Move it 1, 2, 3, 4, 5, 6, 7 places. So this would be 1.4 times 10 to the 7 centimeters cubed. That would be the best answer. If the number you start with is bigger than 1, the exponent is going to be right here, positive. All right, now we're going to review addition and subtraction of sig figs. So where I want your answer to be in milliliters, so we have to convert this liters into milliliters. So 0.0056 liters. There are 1,000 milliliters in 1 liter. So we're going to multiply by 1,000, which is 1, 2, 3, 5.6 milliliters. 5.6 milliliters. So I'm going to mark through this, and this is 5.6 milliliters. Now this original number had only 2 sig figs because leading zeros are losers. This number also has 2 sig figs. So we did it correctly. Remember, significant figures do not come from the multiplication units. From the conversion factors. They come from the measured value. Now I can do the math to put all these together because they have the same units. Okay? So let's I gotta scoot this over a little bit. 405.78 minus 5.6 plus 34.1, 434.28. So my raw number is 434.28. Let me double check and make sure that I wrote it down right. 434.28, good. All right, now I got to check for sig figs. Since I added and subtracted, I look at precision. This first one goes to the thousandths place, or tenths, hundredths place. This goes to only the tenths place, and this goes to the tenths. So the tenths place is less precise. The number has to go to the tenths. So I look, and that's an 8. Round the 2 up. 434.3. So 434.3 milliliters. There will be some questions like these on the test because we've got to get this down. All right, let's review sig figs, just figuring them out. Remember the Atlantic Pacific rule. If it has a decimal point, you come from the Pacific and you count, and it has to have a unit. Must have a unit. So this is 3 sig figs. Again, come from the Pacific. Leading zeros are losers. 1, 2, 3, 4 sig figs. It has the unit meter. This has a unit seconds. Leading zeros are losers. There's none, but 1, 2, 3 sig figs here. This has shoes. That's not something we measure. That's something we count. So 34 shoes is not applicable. There's no significant figures in 34 shoes. This says atoms. Well, atoms are actually something we can count. So again, this is not applicable. Now what about here? This is a meter. A meter is a measurement. So when we have scientific notation with a unit of measurement, we could look at only this portion. So this one has 4 significant figures. I'm going to do one more. 101 grams. Okay? Well, this is no decimal point, so we come from the Atlantic. This has 4 sig figs. One more after that. 2200000 liters. Well, no decimal point, so we come in from the Atlantic. So all these zeros are not significant. 1, 2, 3, 6 unsignificant zeros. This number still only has, 2 sig figs because liters is a measured value. So review significant figures, please, from Chapter 3 and the addition and subtraction. You do need to know all the stuff that's in the Quizlet, so spend time on the Quizlet. I hope this helps. I'll see you soon.